streaming.
Okay, now let's start. Today, it's our great pleasure to have Zhou from Boston University. Shiyu is a PhD student from Claudia Chamal's group, and she's both a theorist and also an experimentalist. I know her work probably a few years ago, where she, together with Claudia, has some amazing work on how to use combinatorial gauge symmetries to view different types of quantum spin liquid and stabilizer code. Today, she will talk about realizing Z2 quantum spin liquids using quantum simulators.
Well, thank you very much for the introduction. And I would like to thank Yiji very much for the invitation and for giving me this opportunity to talk about our work on realizing the Z2 quantum spin liquids using quantum simulators. So this work has a couple of collaborators, and I would like to start by thanking my collaborators. Claudio Shimon, who is my advisor at Boston University, Danny Dao, who used to work at D-Wave but now is at Code Quanta, is another quantum startup, and Dimitri Green, who works closely with Claudio, and Oli Hart, Maria are used to be the students of Claudio Castanova at Cambridge. Now Oli is at UC Boulder as a postdoc. Maria is a PhD student at Stockholm. So in this talk, I will start by giving you a little bit introduction of what are quantum simulators and what are Z2 quantum spin liquids. And then I'm going to talk about the physically realizable quantum spin liquid model and its realization in the D-Wave machine. And then the second part of the talk, I'm going to focus on telling you how to probe the fractional statistics of quantum spin liquids in the quantum simulator. And at the end, I would like to give you a summary and an outlook. So quantum simulators, there are in general two types of quantum computers: digital acts on quantum gates, analog quantum computer that acts on the quantum Hamiltonians. These are the two examples: digital acts on the quantum gate, analog acts on the quantum Hamiltonians. What are quantum computers known for? Perhaps they are best known for solving some very difficult tasks, for example, factoring using Shor's algorithm, and or perhaps solving some optimization problems, for example, the traveling salesman's problem. But for us physicists, the most interesting perspective of quantum computers are probably to simulate the very complex physical systems that are very hard to simulate in the classical computers, for example, quantum spin liquids. So what are quantum spin liquids? In general, people know them as the ground state do not have any magnetic order. But that's not enough, because there are plenty of states do not have magnetic order on the ground state. On top of that, their ground state also displays topological order. So what are the typical examples of quantum spin liquids? There are a couple of solvable examples. Toric code, first proposed by Kitaev on 1997, Fractal by my advisor Claudio Shimon on 2005, and Kitaev honeycomb model by Kitaev around 2006. Even though there's a long history about quantum spin liquids and there's a rich theoretical understanding of quantum spin liquids, till now, finding unambiguous signature of quantum spin liquids in natural material is still ongoing and challenging. So another way to do this is to simulate such states in quantum simulators. Recently there has been two attempts to realize the Z2 quantum spin liquid in the quantum simulators, one done by the Google using superconducting qubits, and the other one done by Misha Lukin's group at Harvard using the Rydberg atom systems. Here, what we want to provide is another perspective, which is to realize the exact Z2 quantum spin liquid states as the ground states of a static programmable Hamiltonian. I know many of you are probably pro on Toric code, but let me just quickly brush over Toric code, which is perhaps the most famous example of quantum spin liquid and is also known to be the Z2 quantum spin liquid. So the Hamiltonian of the Toric code consists of two parts, the star operator and the plaquette operator. The star operator is product of sigma z on the star and the plaquette operator is the product the sigma x on the plaquette. So there are a couple of very nice properties of the Z2 quantum of the toric code, which is that the plaquette operator and the star operator, they all commute to each other, and hence they commute to the Hamiltonian. So by that, we know the ground states of the toric code has to be the plaquette operator and star operator being equal to 1. So that gives rise to the loop configurations shown in the graph. So the ground state of toric code basically is the superposition of all possible loop configurations on the torus. And notice that in this graph, there are two open strings. Open strings gives rise to excitations. And there are two types of excitations in the Z2 quantum spin liquid. We denote them as Spinon or vison. And the one is generated by the open product Z string, and the other is generated by the open product X strings. So notice that the Hamiltonian of toric code consists of 4-body interacting operators, but many of the available analog quantum computers, commercially available analog quantum computers, only provide 2-body interactions. So how can we realize a 4-body interaction Hamiltonian in a 2-body interacting machines? So back in 2019, pre-pandemic time, Claudio, Dimitri, and Zhichen proposed this framework, combinatorial gauge symmetry, to realize the exact Z2 local symmetry in the Z2 quantum spin liquids, while also preserving the spin half algebra using only 2-body interactions. So here's how it works. Rather than having this conventional star term, we have, for a single star here, we have 4 gauge spins colored in green on the link and 4 matter spins mu sitting on the vertex. So the star Hamiltonian is basically the interaction of the sigma term with gauge spins and the matter spin. Notice that the sigma spin, gauge spin, do not couple to the rest of the gauge spin, but only couple to the matter spins. So the way they interact with each other is through this W matrix, which gives out this combinatorial gauge symmetry. What it really does to the end is that gives the spin permutation and spin pi rotation for the Z2 case. For example, for a gauge spin, it couples to the nearest matter spin anti-ferromagnetically and coupled to the rest of the gauge spins ferromagnetically. So basically, this framework allows us to have the gauge spins not directly talking to each other, but rather talking to each other through this matter spins in the middle. So then we can connect all of the stars together to form the square lattice. The Hamiltonian is basically the sum of all of the star terms. And the quantum fluctuation comes from the transverse field gamma tilde on the matter spin and the transverse field gamma on the gauge spins. In the limit, when gamma tilde is much, much larger than J, we can effectively integrate out the matter spin sitting on the vertex and derive this effective Hamiltonian, where the first term is the star operator in the toric code. And to recover the toric code limit, one only needs to realize that the lowest surviving order in the perturbation theory of gamma over lambda is exactly the plaquette term in the toric code. So this has been confirmed by ED and by simulations, specifically exact diagonalization and QMC, where the red curve is the theoretical prediction and the cross here is the ED data and the circle here is the QMC data. So this plot shows us that indeed this combinatorial gauge symmetry Hamiltonian has a Z2 quantum spin liquid phase. And this simulation is done by Kai-Xin Wu shared by Anders and Claudio's group. So now we have this combinatorial gauge symmetry that helps us realize the exact ground state of the Z2's quantum spin liquid. Now we are ready to implement it in a quantum simulator. And the quantum simulator we chose back then is D-Wave. So there are a couple of reasons why we chose D-Wave. It's highly programmable and it has a lot of qubits. Back then in 2019, there's not many choices you can do the quantum simulators on. So the Hamiltonian of D wave consists of two parts. The first part is the transverse field governed by the parameter AS. The second part is the Ising part, controlled by the parameter BS. And the longitudinal field and the ZZ couplings are the programmable parameters in this Hamiltonian. So D wave is known as the quantum annealer. So the quantum annealing is realized by slowly adiabatically tuning the AS and BS, where at the beginning of the experiment, AS is in its largest value and BS is 0. So your qubits are in the ground state of the product state in the X spaces. And as we start the annealing process, we adiabatically tune down the AS and turn up the BS. At the end, AS is 0, BS is at its maximum value. The qubits are supposed to be in the ground state of the Ising Hamiltonian that you programmed into. So this is just a picture of the D-Wave 2000Q chip. It's quite small. It's probably the size of your thumbnail. It has in total 2048 superconducting qubits, and they connect to each other through this chimera graph. So in this chimera graph, there are 16 by 16 unit cells, and in each unit cell, there are 4 horizontal qubits and 4 vertical qubits. So one of the challenge we face is to how to embed our Hamiltonian into this highly restricted chimera graph. So the solution we came up is this embedding called tilted embedding. In the interest of time, I'm not going to bore you the detail of this embedding, but I would like to stress that in order to realize embedding, we have to make 4 qubits to effectively represent 1 gauge space. But I also would like to say that even though we use the 4 qubits to represent 1 effective gauge space, the combinatorial gauge symmetry is still respected. All right, now we armed with all of the parts we required to do the experiments. Now we can do the experiment in D-Wave. So the experiment, before that, I would like to say it's very interesting that EG introduced me as an experimentalist, which I kind of agree, although I'm sitting in the theorist group, but a large part of my job is actually to work with actual device. But I did the experiment when back in the lockdown. I was sitting at home with my 2 pets, and the actual device I'm working on are actually sitting in the Los Alamos National Lab. So I sit at home, program all of the embedding details, and also along with instructions of how to do the quantum annealing and how to reduce the possible errors in the qubits and send it to the D-Wave at Los Alamos through API. And then the D-Wave conducts the experiments and measures at the transverse field zero transverse field limit in the Z basis of each qubit, and send me back the ±1 value of each qubit. Recall that we have to use 4 qubits to represent 1 gauge space. So the transverse field on the gauge space should be to the 4th order of the transverse field on the matter space. So this is what we expect to happen inside of that black box. This experiment starts at the transverse field very large limit, and we slowly anneal down, turning down the gammas. And then at some point, we expect to cross the phase transition between the paramagnet and the Z2 quantum spin liquid, and landed at the classical endpoint of this annealing path, where the measurements can be done. So here I'm presenting a typical sample from the data acquired from D-wave. So here, each bond represents a spin. Gold color represents spin up, and black color represents spin down. And there are the white areas in the middle of the sample. They are the broken qubits of the D-wave we were using in the Los Alamos lab. So we can see that here, all of the spins in the sample, they align to each other, try to form this connected string. And those strings, they either terminate at the internal boundary or they terminate at the external boundary. For example, this one. This one starts in the internal boundary and traverses a long way and ended at the external boundary. So with that, with this visualization and the fact that we have connected strings, we are fairly confident to say that at least we realize the classical version of the quantum Z2 spin liquid in D-wave.
What's the reason why you have an internal boundary? Those are the effective qubits?
Yes, those are the broken qubits. But we can do more. By deforming the diagonal elements of the interaction W matrix, we can realize both spin ice and the ferromagnetic states. So eta is the amount of deformation. So when eta is negative, we can realize spin ice states. When eta is 0, we recover the Z2 spin liquid state. But when eta is positive, the extreme example is when eta is equal to 2, this W matrix just becomes all plus, where we get the ferromagnetic states. And these are the samples. So panel A is the state I showed from the previous slide. It's the Z2 spin liquid state. And panel B shows the spin ice states when eta equals to -0.2. And one strong indication of the state being spin ice is that you do not see any self-intersecting loops in this configuration, which strictly follows the 2-in, 2-out ice rule. And panel C and D shows the ferromagnetic states when eta equals to 0.2. C is an example of all spin down, and D is an example of domain wall separating all spin up and all spin down. Furthermore, we can study the transitions among those 3 different phases or states by realizing that classical Z2 spin liquid is basically an 8-vertex model. We further separate, meaning that each vertex just need to satisfy the parity equals to 1 constraint. We further separate the 8 vertex into 6 vertex and 2 vertex, which the 2 vertex gives us the ferromagnetic states, and the 6 vertex gives us the spin ice states. And we map out this phase transition where the x-axis is the eta, is the deformation of the diagonal elements of W matrix, and the y-axis is the temperature. And the orange line separating the spin liquid and ferromagnetic case, and the spin ice lies at the line when eta is negative. Notice that there is a dashed box in the middle. That's the experimental realizable regions in D-wave, because we cannot reach absolute 0 temperature at D-wave. And here I'm showing you the experimental data from the D-wave. The x-axis is eta, the y-axis is the effective temperature by tuning the couplings. And what we measure here is the density of 2 vertex. When density of 2 vertex is equal to 1, we have the ferromagnetic case. But when density of the 2 vertex equal to 0, we have the spin ice situation on the left. And then exactly when the density of the density of 2 vertex equal to 1/4, we have the 8 vertex model. Furthermore, what we can calculate is the density of every single vertex. So on this plot is showing x-axis or the deformation, y-axis is the density of every single vertex. And then you can see that when eta is negative, the probability of seeing the 2 vertex is heavily suppressed. But we have the 6 vertex being almost equally probable. But when eta is positive, the probability of seeing the sixth vertex is heavily suppressed, left with this 2 vertex probability. But exactly at eta equal to 0, every single vertex is equally probable. That is a strong indication that we realized the classical endpoint of the quantum Z2 spin liquid. Rather than saying, well, we can just say that we realized the classical Z2 spin liquid. But exactly like I said, we have been realizing the classical version of the quantum Z2 spin liquid, but can we actually observe any signatures of quantum spin liquid in the quantum simulators? The answer is yes. So one of the defining features of quantum spin liquid is that the ground state has topological order. So the excitations of the quantum spin liquid has fractional statistics. So here I'm going to show you how to probe the fractional statistics of quantum spin liquids in quantum simulators. To do that, we propose this quasi-1D Z2 ladder structure, where the Hamiltonian is the usual Z2 lattice gauge theory, but the two adjacent stars now share 2 spins to form this quasi-1D ladder structure. And this model is known to have 2 excitations, Spinon and vison. The Spinon lives on the star. It is basically the energy violation of the star operator. The energy scales at lambda. And then we also have vison. It's basically the violation of the plaquette term. And you can think of it as a pi flux thread, the plaquette, threading the plaquette. And its energy scales as gamma squared over lambda. And furthermore, we consider the finite temperature region where the temperature sits right in between the vison gap and Spinon gap. And in that situation, the energy formation of vison is much lower than the temperature. So we can think of visons as stochastically locate at random plaquettes. Furthermore, when we turn on the transverse field, the Spinon acquires dynamics in a timescale much longer than the visons. So the visons in that situation can be considered quasi-static as well. So in this temperature region, visons are basically stochastically locate at random plaquettes and are quasi-static. With that, we can propose the following experiment. Imagine we have a Z2 ladder, and we initialize a single Spinon on the ladder. The Spinon can propagate freely along this ladder when there is no presence of vison. However, when there is vison present in the chain, the top and the bottom path for Spinon to travel to the star, to the nearest star, acquires 2 opposite phase, plus minus 1, which gives rise to this destructive interference pattern. So effectively, what happens here is the presence of vison cuts the chain into different segments and makes Spinon localized. And furthermore, we can freeze the bottom leg of this ladder by, for example, applying a very strong longitudinal field to freeze the spin on the bottom legs. In that situation, even with vison's presence, the Spinon can propagate freely along this whole chain. So with the bottom 2 experiments, we can very easily detect if the states we realized in quantum simulators are Z2 quantum spin liquids or not. Because if it is, then those 2 situations should give you very different phenomena. The middle one, one should observe Spinon localization. The bottom one should observe the Spinon just propagate. However, if the states you realize in the quantum simulators are not Z2 quantum spin liquid, those 2 situations should give you the same exact results, which is the Spinon propagating along the whole chain. And we further study this phenomena against the disorders and dissipations by mapping the spinon hopping along a ladder to spinon hopping along the chain. So here gamma is the hopping amplitude, and the B dagger B is the boson creation and annihilation of a single spinon on site S. The hopping amplitude between two adjacent sites indicated by the bond here can take two different values here, 1 and 0. If it's 1, that indicates the absence of vison. If it's 0, that indicates the presence of vison in a clean environment. On top of that, we can add disorders. We can add both diagonal disorder and off-diagonal disorders. And the disorders are Gaussian distributed with 0 mean and standard deviation sigma 1, sigma 0. So here, what I'm showing is the spinon dynamics against the time. So the x-axis is the time, the y-axis is the mean square displacement of the spinon. So the blue curve indicates the situation when there is no interplay of vison-spinon statistics. As you can see that the spinon ballistically travel to the end of the chain. However, when there is vison, the spinon does not travel more than one lattice side apart, and the mean square displacement of the spinon basically saturates around one lattice side. So such distinction persists up to very large diagonal disorder. However, this distinction will become weaker and weaker as we turn up the off-diagonal disorder. And when the off-diagonal disorder is on the order of the hopping term, basically distinction disappears, the two cases merge. On top of that, we study how the vison dynamics will affect the spinon dynamics as well. So previously, we assumed the visons are static, but however, in the current devices, quantum computers, we always have some kind of noise. So in this situation, any kind of z-directional noise would make vison hop, and the vison will acquire some dynamics. So here we study the stroboscopic dynamics of vison and study how it affects the spinon dynamics. And delta T here indicates the rate of updating the vison configurations. So when the delta T is very large, that just basically means the visons are not moving. But when delta T is very small, that just means visons are constantly moving around. So as you can see that when we turn down delta T, allowing more and more vison dynamics to kick in, the spinon localization phenomena slowly to disappear. And at late time, the spinon basically travels to the end of the chain. All right, so we proposed such experiments, but we want to realize this quasi-1D Z2 ladder in the actual device. To do that, we constructed this quasi-1D combinatorial gauge symmetry ladder, we denote as CGS ladder, which is basically where we have to put the extra 4 matter spins in the vertex to allow this two body interactions, and that give us the exact Z2 local symmetry. So this ladder also has the exact Z2 local symmetry that is generated by the operator GP. So basically GP is the product of 3 different operators, FPL, BP, and FPR. So BP is basically the product of sigma x on the plug end, and FPL and FPR acting on the matter spins on the left and the right of the star. What do they do? They effectively just permute and flip the matter spins on the left and the right stars. It's also not very hard to show that the GP operator squares to 1, and they also commute to each other. And then we did implement the quasi-1D ladder into the D-wave machine. In this situation, rather than having 4 qubits represent 1 gauge spin, we have this 2 qubits represent 1 gauge space. And then we did the embedding and set up the experiment, but we faced the 2 challenges in D-Wave. First, the D-Wave operating temperature, which is around 13 to 15 millikelvin, is still too high, in the sense that this temperature is larger than our hopping gamma term. That already kills what we want to see. And second, the characteristic time scale for our experiment happens at nanosecond, which is much smaller than the microsecond time scale that is available in the commercially available D-Wave machines. So with that said, I would like to conclude. I guess I didn't use much time, but with that said, I would like to conclude my talk by giving you some summaries. First, I would like to say that we designed Hamiltonians with the combinatorial gauge symmetry using only local pairwise interactions where the exact quantum spin liquid states are the ground state of the static Hamiltonians. And then we realized the classical endpoint of the Z2 quantum spin liquids in D-Wave. Furthermore, we proposed a smoking gun experiment to detect the thermionic statistics of quasiparticles in the Z2 quantum spin liquids in quantum simulators. So right now, what we are trying to do is that, okay, it doesn't realize in a D-Wave machine, but is it possible to detect such fractional statistics of Z2 quantum spin liquids in the IBM machine? With that, I would like to thank all for your attention.
Thanks for the very nice talk. Any question here?
How about the Rydberg atoms machine from Cura?
Yes, everyone asked this question. Of course, that's the first alternative, and then D-Wave came to our mind as well. And then we actually reached out to folks from Cura asking if it's possible to realize the combinatorial gauge symmetry. But the interaction in the Rydberg atom is van der Waals interaction, and it's only positive. And however, in our case, we have to realize both positive and negative interactions. And it's not possible. It's not impossible to do in the Rydberg, but you need to use, for example, 6 to 7 qubits to realize effectively 2 qubit interaction for ferromagnetic and both ferromagnetic interactions. And that is very cumbersome for our situation because on top of that, you have to think of the unit disk interaction of the Rydberg blockade radius. And it becomes basically to the end, we realized embedding is very hard to do, to embed our Hamiltonian into the Rydberg atoms. Yeah, we thought about it, but I think it's probably not possible at this stage. Yes.
So about the limitations of the D-Wave machine for your simulation, so I think that for me, the temperature scale limitation makes a lot of sense. But what characterizes the time scale limitation of the D-Wave machine?
That's a great question. So what happens is that the D-Wave, if you work with them, you will have the nanoscale availability to do the experiment. But here, our temperature basically kills what we want to see anyways. So
quasi-particle names are usually pretty clear to understand. What does vison come from?
Oh, the name?
Like Spinon makes sense and exciton makes sense, but what is a vison?
The name, or maybe is it coming from a high energy field theory perspective?
You have a tail of the vison string.
The tail of the vison.
Yeah, because you need a string operator to generate it, and that line is the vison line.
Yeah, but sure, but I guess he's asking where is the name coming from? Yeah, but I don't know where's the name coming from, but like E.G. said, it's basically the way you can understand this excitation is the open string.
Thank you.
Yeah. So
Going back to the temperature, can you increase the gap?
the gap of our model?
Right.
No. Yeah. Which gap you're talking about?
I suppose, I mean, what is your gamma there? What does it represent?
So so gamma here and here represents the hopping. We can, what we did is that we have to do a couple of mappings from the CGS model, which is the one exactly realized in the D wave, to the 1D ladder. I actually didn't talk about it, but we have a exact one-to-one mapping of those two models. The temperature we are comparing here is the splitting of the spinons. That gives you the hopping. And if the temperature is larger than that, we basically cannot observe the things we want to observe. And for doing that, we of course can tune gamma to be different values, but in the D wave machines, tuning gamma we also tune the coupling of ZZ. They are correlated, so we have to find a sweet spot where gamma is not too small, but also J are not too small either, because by tuning up gamma, you're tuning down the J couplings as well. So we tried to find such sweet spots that the temperature is below gamma and below the J, but we couldn't find it. So
Thank you.
yeah.
I'm just curious about moving this to like IBM's system, like you mentioned. Do you need as many qubits for doing that as the D-Wave? Because I don't think they're quite at 2,000 or so yet.
Yeah. So we will take a completely different approach if we want to simulate this. First of all, we don't have to use the combinatorial gauge symmetry anymore. What we need to do is we need to realize if we can realize the exact state of one single Spinon state, and then you do the characterize the time evolution on the IBM, we should be able to see this. Yeah, exactly like you said. We don't need to worry about this two-body interaction, four-body interaction, because you can actually characterize decompose the sigma ZZZ fourth sigma Z term into a series of C naught and then Z direction rotation. Yeah.
Actually, I have a question. Is it possible to implement the ZZ interactions or the transverse field in a Floquet manner where it can time oscillate? Because for stabilizer code, the problem is we need some cluster interaction. Here, what you do is you try to effectively generate cluster interaction. But for lots of Floquet stabilizer code, like Floquet Toric code, what would happen is in each step, all they need is some type of two-body interaction.
So what you are saying is that
it's something like on the first step or the first time period, we just have ZZ interaction between two qubits, and then the second period is just sigma x, and then another type of ZZ interaction, something like time period.
Yes, I think it's a very nice idea. It's probably not going to be realizable in a D wave because once you set up your couplings, because I would imagine like a ZZ and X and the ZZX, but once you realize your coupling here, you cannot change it. It's global. But that does not say that we cannot realize in a digital quantum computer where you have much more control over, let me apply ZZ and let me apply X and let me apply ZZ to realize this Floquet thing. But I think this is a really great, yeah. Or maybe one can even think about if we can do that in the Rydberg system, right? If in the lab level you have more control, yeah, and then you probably can turn down Rabi frequency and turn up and turn down. And if you can move atoms around to realize the ZZ coupling, well, it's not exactly ZZ coupling there. So yeah. Yeah, I never thought about it, but I think it's really cool.
Yeah, thanks. Any other question or question from the audience? No, then let's thank Shiyu again.
Thank you very much.